So we have in parentheses x squared plus secant squared. So what we want to do here first is well, pretty much what we did in number 5, except without the algebra. All we have to do is split up our integral, or at least think of the two components as two separate functions that we're integrating. Right? And so once you do the split, you can integrate each part separately. The first part is procedural, the second part is fact. All right? So the antiderivative of x squared is x to the third over 3 plus c, but let's hang on to that in a second because we're going to consolidate our c's in a minute. 10x. And then plus this. Okay, so this part gave us the blue, this part gave us the red. All right. The second part, again, is just knowing the fact. And so I don't have to give you a list of antiderivatives. I mean, you can look in textbook tables, things like that. Antiderivative rules are really no more complicated than knowing the derivative rules. So I don't have to give you a list of, like, the antiderivative of secant squared is this. And besides, the reality is, if I were to create a list, I don't think secant squared is making the cut. I think I'm going to stay with the 6 trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. All right, those would be the fact-based ones that I'd want you to know. But if I do know that the derivative of tangent is secant squared, then whenever they ask me for antiderivative of secant squared, I know it has to be tangent. All right, so know your derivatives, and you'll, in turn, have a leg up on knowing your antiderivatives. All right, number 7, we want to do the splitterooski here. But then we also want to make some adjustments. All right. When you were finding derivatives and you were given a radical, the first thing you did was convert it into power form. It's the same idea for antiderivatives. So instead of saying the square root of x, I'm going to say x to the 1/2. Now, we haven't actually found the antiderivative yet, so we'll hold that thought. But it'll be much easier to do once we get this in the proper order. That 1/2, regardless of what's in the bottom with the 2, it still is a multiple of 2. So what I'm going to do is I'm going to look at this as a coefficient of 1/2. And then I'm going to change the x squared, which is on the bottom, into something else. That would be x to what power? Negative 1/2 power. Okay? And that's because it's on the bottom of the fraction. All right? So to move it up, we negate the exponent, and because it's a radical, it becomes power of 1/2. If it were a cube root, the power would be what? It would be negative 1/3 if it was on the bottom of the fraction. All right? So now we can get into the act of actually finding the antiderivative. Increase the exponent by 1, divide by the new exponent. So if a question doesn't ask you to simplify, it could look pretty ugly when you do this. So x to the 3/2, and then divide by the new exponent, divide by 3/2. That doesn't look very nice. I'm not overly thrilled with that, but you know, it didn't say simplify in the directions on a test, for example, so you can technically leave it this way. But instead, I'd rather write it as 2x to the 3/2 over 3. That took off on there. Or, yeah, it's just like tailing off for no reason. 2/3 x to the 3x. Either way is fine. The one way you don't want to represent it is the first way I wrote it. And that's because if you had to do something with it, that's not really the nicest way to have it. You want to have something a little bit simpler. The third way that I wrote it was the best way, because if I had to find an antiderivative again, it's already in power rule form, so we're looking pretty good at that point. Now the second piece, again, we're increasing the exponent by 1, so the negative 1/2 is going to become a positive 1/2. And then divide, because there is a coefficient of 1/2, divide by the new exponent. In which case, this just is going to boil down to x to the 1/2. And then add them together, bring down your positive sign, and then tack on a plus c so you don't throw away easy points. All right, so again, increase the exponent by 1, divide by the new exponent. You don't have to show all the intermediate steps. You can just jump right to the final answer if you're comfortable with that. But I know some of us aren't. You want to even if you are comfortable with it, you still want to kind of make sure that you're fluent in it. So to the point where it like kind of minute math back in elementary and middle school, where it's like you just do as many problems you can in 1 minute. It's the same idea here. It should get to a point where it becomes so second nature, where I say, what's the antiderivative of 2/3? You're not like, okay, what is 2/3 plus 1? Divide by that. What's 1 divided by that? Let me get my calculator. If you could get to a point where you just can know it, then everything that comes after that is going to be that much easier. All right? But if not, that's okay too. You'll be able to get answers, but you want to kind of expedite the easier stuff, quote unquote easier stuff. All right, 2t squared minus 1 squared. Now we have not learned to use substitution in this course yet, so or trig substitutions or anything that might be able to handle this type of integral with a differing approach. There's a much simpler way anyway. Yeah, expand the polynomial. Yeah, distribute that bad boy out. All right, so if it helps, write it as 2 separate binomials in FOIL. But this is what you should come up with. And then you can integrate each part, because each one of these components is its own power rule. But if, like me, after a certain point you start getting a little sick and tired of rewriting the integral just with rewriting the components of the integral, each with their own funky s and dx. I mean, if you don't want to do that here, you can just know that that's really its own integral, so is that, so is that, rather than writing integral of this dt minus integral of this dt plus integral of that dt. All right, so you can kind of skip that little step in the middle there. All right, so reverse power rule in each case, increase the exponent by 1, divide by the new exponent. So what's my first one going to be? Exactly. What do we say? Oh, this is going to be blue, sorry. Yeah, my color scheme right here. So minus 4 thirds c cubed plus c plus it's one of those things like I think personally, or at least from experience, that people kind of fall into 2 categories. The kind of people that are going to remember to everybody falls into 2. Of course, that's just like no, it's not even remotely like that. But just to kind of be simplistic about it for a second, let's say people fell into 2 categories. One of them would be the kind of people who forget the plus c, and the kind of people who never forget the plus c. In my experience, the people who never forget the plus c never forget it because they know why it's there to begin with. They understand its purpose. The people who forget the plus c never really connected why the plus c was there to begin with. And so it became just a memorization step. I know that I just have to do a plus c at the end for some reason. You know, so if you have a good, solid understanding of why that plus c is there, then you'll never forget to include it. You'll never have to worry about losing credit. And again, just to elaborate on that, it's there because this answer could have been 4/5 c to the fifth minus 4/3 c to the third plus c plus 1. If I took the derivative of that, I would get this. It could have been 4/5 c to the fifth minus 4/3 c to the third plus c plus 7 minus I plus e plus pi squared plus the sine of 47. It could have been any numerical value. To allow for that fact, we put a plus c there. We put a catch-all for all possible numbers that could have been in that position to allow for this to be a true antiderivative.